Hi everyone, thanks for joining this virtual session. We are going to talk about how to run Flink on Kubernetes natively. A brief introduction myself. My name is Wang. I come from Alibaba and have more than 5 years experience of big data and distributed system. Now, I'm mainly focused on Flink deployment and operation in production on a large scale. This is today's agenda. First, I will quickly go through introduction of Kubernetes, including the architecture and some basic concepts we will come across in Flink. Second, I will review the effort what the community has done for the Flink on Kubernetes. Next, let's do a deep dive into the technicals about how the native integration works, and followed by a demo. Finally, I will share some production practice. Okay, let's start with some background about Kubernetes introduction. So, what is Kubernetes? This is the most succinct definition. I copied from the website and picked some key things to remember here. It is open source in 2014 and used for management of containerized application at scale. And provides the simple declarative API for users, and all the operation will be done automatically by Kubernetes internally. It is cloud native, and almost all cloud providers could support out-of-the-box Kubernetes cluster. This is the architecture of Kubernetes. It is a very typical distributed master-slave architecture. The master node is responsible for managing the Kubernetes cluster. It consists of various components including API server, the etcd storage, the controller manager, and the scheduler. The API server is the only entry to access the Kubernetes cluster from user side. For example, you could use kubectl or dashboard to communicate with API server to create a deployment with 4 replications. Then, the API server will process the request and store the state in the etcd. The scheduler knows the resource usage information for each workload and also know about constraints that the user may have set, so it will assign port to the appropriate node. The Kubernetes cluster consists of a set of work which called nodes. It may be physical or virtual, on-premise or on-cloud, that host applications in form of containers. It consists of Kubernetes, kubeproxy, and container runtime. Usually, we use Docker for container runtime. Now, let's take a look at some key concepts of Kubernetes. The first one is config map. It is a dictionary of configuration settings. This dictionary consists of key value pair of strings. The common use case in Flink is creating the config map from the configuration files, such as Flink conf YAML, Log4j properties, Hadoop configurations, and then mount them into the pod. The second is service. Service is an abstract way to expose an application running on a set of pods as a network service, especially when you want to access a pod from outside of the Kubernetes cluster. The service seems to be the proper way. In the Kubernetes cluster internal, the service could also be used to avoid the pod failure and IP address change. You could always use a stable service name instead of directly using the pod IP. The next is pod. It is the smallest deployable unit. It contains one or more Docker containers, and the container may have different life cycle. For example, you could use init container to do some initialization work, downloading some dependencies, updating the configuration, and so on, and use a sidecar container to collect the logs to persistent storage. The last one is deployment. It is a high-level abstraction to manage a set of identical pods. It helps to keep the desired replication of a pod For example, we could use deployment to start 4 task managers. When anyone exists exceptionally, the deployment controller will compare with the desired state and reconcile constantly. So a new task manager will be started to replace the old one. Another cool thing is Kubernetes is versatile, and if you just look at the diagram in the left, a whole bunch of web or mobile status applications already used to run on Kubernetes. For example, Index, Apache Web Server, and so on. Increasingly, we also see many people are trying to run storage workloads which have a stateful component like MySQL, Elasticsearch, and Kafka. In the recent years, the deep learning is so popular, and most of the workloads of TensorFlow are running on Kubernetes. The big data seems to be the last one to join the party, but I think it is a very important signal, since we always believe that they are more appreciate running on Hadoop cluster. So overall, this picture, you could run all workloads on a single cluster, and that not just improve the utilization of the whole cluster, but also we will not always need to manage multiple different scale clusters for various use cases. I think many of you have tried to deploy Flink on Kubernetes. Even some users has already put it into production. In this part, I will try to conclude the current option to deploy Flink on Kubernetes cluster. Before this, let me try to give some reasons for why do we need to run Flink on Kubernetes. The first is about a container environment. It is easier to set up an exact same environment with a local. It is reproducible. If you use the same command, then a same runtime environment should be ready for you. Before the container, we always suffer a lot from the machine environment. My application runs pretty well until someone other guys install new software or update a new version of system software. When I want to debug my application, I can't do it because the cluster environment has changed. The second is multiple tenant support. Kubernetes could give us better isolation, not only for the resource, but also for the network and security. The third is about mixed workloads. We always hope to run all workloads in a unified cluster, including the web server, storage, deep learning, and big data applications. Then we will not manage multiple different clusters, for example, YARN, Mesos, standalone, and more. Also, we could have better resource utilization. The last one is we could leverage the fast-evolving Kubernetes cluster ecosystem, including the network performance, log collector, monitoring. These tools are open source and could be used out of the box. Now, let's see how could make Flink and Kubernetes work together. The straightforward way is to deploy a standalone cluster on Kubernetes. We will not need to change any code of Flink, and we just write some YAML files to create the Kubernetes resources. If you are running more jobs in a session cluster and find that resource is not enough, then you need to use kubectl to scale up the task managers. Also, some of you could use the GCP or AWS autoscaler. Next, we come to the first improvement, standalone job. Mostly it is for isolation. Flink has a standalone job cluster entry point, so we could use it for startup job of Flink cluster. In this case, you need to build your own doc image to bake in the user jars and dependencies. The job cluster is a one-step submission. We do not need to wait for the Flink cluster ready and then submit the job. Another important thing is the user main code is executed in the cluster, not the client side. Now let's take a look at the next improvement, Helm chart. If you feel it is still complicated to apply so many YAML files, then the Helm chart is appropriate for you. Helm is the first application package manager running atop Kubernetes. It is very similar to the YAML in the CentOS or Red Hat Linux. You could use you could simply use Helm install to start a Flink cluster. However, currently the repository is outdated. Next, we will use Operator as a control plane to manage all the Flink applications. Operators are software extensions to Kubernetes that make use of custom resources to manage applications and their components. Operators systematize human knowledge as a code. It could help us to make the Flink cluster deployment easier. Also, it could support multiple Flink cluster management and whole lifecycle management for each application, including configuration update, user code upgrade, restart, and so on. For example, if you upgrade the user code, the Flink Kubernetes operator could help to trigger the same point and restart from the latest successful same point. Currently, Lyft and Google open source their operate in the GitHub. They are both great work to make Flink on Kubernetes running in production. You could check out them and have a try. Now we have reviewed all the efforts that the community has done for Kubernetes Flink Kubernetes integration. However, we still have some limitations. The first is Flink is not aware of underlying Kubernetes cluster. All the work is done out of Flink. We use kubecontrol, Kubernetes dashboard, operator to create a job manager and task manager and mount the configurations. The second is static resource allocation. The Kubernetes will always retain specified number of task managers running, no matter whether there are jobs running or not. The third is user requires some upfront knowledge about containers, operators, or some environment-specific tools like kubecontrol, because it is very important for them to get started. The last one is that user need to calculate the resource requirement beforehand. If you are running a batch job or multiple jobs in a certain cluster, it will be difficult to determine how many task managers are needed. So I think it's time for the native integration with Kubernetes. Here I want to uh, emphasize two important points. First, we are not going to replace the standalone on Kubernetes, since the standalone mode is mostly for reactive mode. Imagine that you have 10 gigabytes memory and 4 cores. So you start 4 task manager with 1 slot for each. The Flink cluster should realize and update the default parallelism to 4. When we get more resources, we hope the Flink cluster could update the parallelism automatically. All in all, how many resources you have determines how fast your Flink jobs could run. Second, we are not going to replace the Flink Kubernetes operator. The operator is focused on Flink job lifecycle management. Frankly speaking, they could work together to make the user have more choices. This is what we are doing internally, developing a new Kubernetes operator which could support native integration. Now let's deep dive into the technical about how the native Kubernetes integration works. Before we begin, I want to talk about what the native means. First, Flink is self-contained. There will be an embedded Kubernetes client in the Flink and will not need other external tools, such as kubecontrol or Kubernetes dashboard to create Flink cluster on Kubernetes. Second, the Flink client will contact with Kubernetes API server directly to create a job manager. The configuration located on the client side will be shipped to the job manager port. also for the log4j and Hadoop configuration files. And third, Flink Resource Manager will talk to Kubernetes API server to allocate release the TaskManager dynamically on demand. All in all, if you are a Flink user and you are deploying Flink on other resource management systems such as YARN, then you will not have any learning curve for Kubernetes, especially you have some internal deployer for multiple Flink jobs lifecycle management. It is very easy to integrate with the native Kubernetes support. Okay, let's start with the staging cluster. Benefit from the refactor of Flip 6. It is not very complicated to add a new support for cluster management. It has the following steps. First, Flink client will connect to the Kubernetes API server to submit the cluster description, including config map specification, job manager service specification, job manager deployment spec, and owner reference. Second, Kubernetes master create a job manager deployment. The Kubernetes will pull the image, prepare, mount the volume, and then execute a start command. After Flink master prod launched, the dispatcher and the Kubernetes resource manager has been started. After step 1 and 2, the first phase has finished, and the Flink session cluster is now ready to accept one or more jobs. Third, user need to submit the Flink job via Flink client. The job graph will be generated in Flink client and then uploaded with user jar through REST client together. Generally, the Flink client and the job manager are running in different network domains. The job manager is running in an overlay network, and the port IP address could not be used by Flink client to create the connection. So we use the Kubernetes service for this situation. The service could be exposed by load balancer on the port. Next, once the job has been submitted successfully, job submit handler in Flink receives the request and submit job to the dispatcher. Then job master is spawned. Job master request starts from Kubernetes Resource Manager. And the Kubernetes Resource Manager found that it do not have enough resource and will talk to the Kubernetes API server to start more task managers to get enough resources. Each task manager is a port with unique ID so that we could release a specific one. The Kubernetes Resource Manager will generate a new configuration for the task managers. Mostly they are memory-related configurations so that the task manager Java process could be started in a proper shape. Next, task manager is launched by Kubernetes. Once the task managers come up, they will register at a resource manager. And then slot manager requests slot from the task manager. The task manager will offer slots to the job master, and the job master will start to execute the job. All the tasks will be deployed and running. Since in the session cluster, all the jobs share a same Flink cluster, if some jobs has memory leak or critical bugs which will make the JVM crash, then all the jobs running as the task manager will also fail. It is not acceptable for different users, especially in the production environment. So we really need the job cluster. The whole submission process is very similar to the session cluster. The biggest difference of the submission is step 3. The user jar and dependencies are already baked in the image. So when the job manager port is launched, the job will be submitted in the cluster entry point. Next, let's compare the session and the job cluster. I hope it could help you to make your best choice in your situation. The first is where the user main code is executed. This is very important when you have some logic to access external system in your main codes. For session cluster, the user maker will be executed on client side and the master side for the job cluster. Maybe in the future we will also support client mode for the job, but now we do not see the requirements for this. The second is how the job graph, user jars, and dependencies are distributed. For session, they are uploaded via REST client and localized by Flink distributed cache. For job, they are all built in the image and could be downloaded by the Kubernetes init container. The third is isolation. Obviously, the job has better isolation since we start a dedicated Flink cluster for each job. The last is about the cluster lifecycle. The session cluster need to be started and stopped manually, so the users are responsible for the lifecycle. For job, it will be created with the job and destroyed when the job finish or be cancelled. So far, we have known how the Kubernetes native integration works. Next, I will show you some demos and hope you have a better understanding. I have prepared some commands beforehand, and all the operations will be executed in a real Kubernetes cluster with version 1.13. Okay, let's get started. First, I will show the session cluster example. Let's copy the command and run in the terminal. In this command, the first argument is class ID. It should be unique and will be used to create Kubernetes-related resources. If it is not specified, the Flink client will generate a UUID automatically. The second is image. You could use the Flink official or your own image. Then we set the memory and CPU for job manager and task manager. By default, it is hard limit, which means you could not use more than allocation. For memory, the pod may be killed by Kubernetes cluster. For CPU, it will achieve the bottleneck and your application may have poor performance. Then we set an idle time of task manager to 5 seconds for the demo purpose to make the task manager could be released as soon as possible. You could convert to a proper value in your case. And last, we set the command template. Also, we add a console log filter appender so that we could use Kubernetes control to view the logs. When the cluster is submitted successfully, URL will show. It could be used to view the Flink dashboard if you are using a load balancer, since the Kubernetes cluster needs some time to prepare for it, so an port address may occur here. Let's take a look at the Flink dashboard. No jobs, no task managers, and no available slots. Let me submit a Flink job to the cluster. The E is for executor. It is a new introduced unified logic for the job submission in 1.10, and you could refer Flip 73 for more information. Now the job is submitted successfully, and the resource manager will allocate enough task manager to run the job. Since we set the 4 slots for each TM, and the parallelism is 10, so 3 task managers should be started since, and we will have 2 available slots after the job is running. In the native integration, the TM is allocated and released dynamically. When we cancel the job and all it finished, what will happen? Let's check it. Yeah, we could see all the TM has been released. Finally, let's quickly clean up the session cluster. You could see that all the operations could be done without any knowledge of control or container. Flink is just self-contained. Second, we come up to the job. The argument is very similar with the app job. The difference is about the user jar. It is baked in the image, not located in my local machine. We could check for that. After the job is submitted successfully, the user main code will be executed on the job manager side in the Kubernetes cluster, and will allocate the task manager dynamically. Now you could see that it is one-step submission. Each job will get a dedicated Flink cluster for running, since the Flink cluster lifecycle is bound to the only job. When it goes to the terminal state, the Flink cluster will be destroyed automatically. So let's cancel the job and see what will happen. Yeah, all the created Kubernetes resources has been cleaned up. Even we use the deployment for the job manager, it will be relaunched when crashed exceptionally. However, Flink does not store the job graph and chain point meta in persistent storage by default. So the job could not recover correctly from the latest chain point. Usually in the production environment, we should configure high availability. Now let's have a try of the high availability in the Kubernetes. The command is almost the same with before, except for the zookeeper related configurations. Here we use HDFS for the checkpoint path, so we should provide the Hadoop configuration. If the Hadoop conf directory is set, the Flink client will help us to create a Hadoop configuration config map and then mount into the job manager task manager port. Let's check the config map. Now the job is running and the checkpoint is successful. Let me simulate the job manager failover and see what will happen. I will use the kube control to kill the job manager process. Now we could see a new container is launched by Kubernetes and the restart count increase 1. Here we need some time for the election and recover. And after a few seconds, let's check the log for restoring. Yeah, we could see that the job has been restoring from the latest chain point successfully. Finally, let's cancel the job. That's all for the demo. Let's come back to the last part of the presentation. The first optimization is native Kubernetes high availability. Why do we need to configure high availability service? It is used for leader election and leader retrieval. It is very common requirements in distributed system. Imagine that we have started multiple job managers, which will make us get a fast recovery when active one crashed, or just one job manager, but a new one is started when old one terminates exceptionally, just like YARN and the current Kubernetes implementation with deployment. We need the election service to get an active leader and publish its address in the config map. Then the active leader will periodically renew the log under so that it could it could keep the leadership. For other standby job managers, they are always trying to get the leadership. Once the current active job manager failed, some one of them will be granted as a new leader and take over all the scheduling and the recovery of the Flink jobs. How the task manager could connect to the job manager. For the high availability implementation, the leader retrieval service will get the active job manager address from the leader config map and then register to it. Also, the leader retrieval service watches the leader config map. When it changed, it could reconnect to the new one. Moreover, Flink also creates the meta config map, which stores the job graph, chain point meta information. Usually, it is a part of the distributed storage. For example, HDFS, S3. Now let's come to the second optimization. It is the log collector and the matrix collector. For the production applications, the logs and the metrics are very important. They could help us to monitor our applications, and when there are some failures, they could help us to dig into and find the root cause. Usually, we provide three ways to collect the log. The first is a log4j to appender. It is what we are currently using in our production. A benefit from the custom appender of log4j2, it is very easy to collect the logs to the distributed storage. In our internal use case, we have a custom appender named with LS appender, which will directly send the log to the client log service. The client log service could provide view, search, and other functions. The second option is sidecar container. It is also a very common use case for Kubernetes service and applications. There are many log collector engines such as Logstash, Flink. The job manager and the task manager could put the logs in an embedded DR and share it to the sidecar container via volumes. The option is more flexible and do not need to develop your own log4j to appender or update the log4j configuration. The third way is to start the log collector engine as a daemon set, so each slave node will have only one agent. The job manager and task manager could mount a host path into the port to store logs. The logs will be cleaned up once it has been collected by the daemon set successfully. For the matrix collector, we do not make any changes to the promises collector. We just start a multiple push gateway and make sure each Flink only send to one push gateway. It is a very simple one-Ruby balance. The last one is the network. The network architecture in Kubernetes is very different from the YARN, since the YARN do not have the network virtualization isolation. All the containers are running in the host machine network. For Kubernetes, it provides an overlay network by default. Each pod will have their own IP address, so in the small deployment and not sensitive about the network latency. You could use a Flannel with a proper backend. However, in our internal use case, we found that for heavy network applications, the performance of Flannel is about 10% lower than the YARN standard deployment. And the Flink job frequently failed with connection reset by peer or some other network problems. So we enable the host network for job manager and task manager port. In such case, we should use a random port for all port range for IPC, REST, and blob ports. And the native Kubernetes high availability could help us a lot in this case for the lead retriever. In the cloud environment, since we need to provide isolation for different users, the host network is not reasonable. Fortunately, the AWS, Google Cloud, or Alibaba Cloud, they both could provide the native VPC networking via the custom CNI plugin for Kubernetes. Using the CNI plugin allows Kubernetes ports to have the same IP addresses inside the port as they do on the VPC network. The CNI plugin is responsible for attaching the elastic network interface and allocating the IP address in the VPC. It could provide the same performance as a host network with excellent isolation. Now we come to the last page of today's presentation. What's the current state of all the just introduced features? First, quantization. It has been released in 1.10 as a preview feature for the users who want to have a test on the native integration. For Kubernetes per job, the community has planned it in 1.11 with the application mode. You could refer to Flip 8.5 for more information about the application mode. For the native Kubernetes high availability, we have an internal implementation and will be used in production. Personally, I also hope it could be contributed to the community soon. Also, some advanced features has been planned in 1.11. For example, a label annotation, node selector, and toleration. Also, for the sidecar in the container, some uncommon features we are considering to use port template to support, including affinity, anti-affinity, volumes mount, DNS policy, and so on. That's all for today's presentation. Thanks a lot and welcome for your question.